All right, for this explainer, we're going to put on our detective hats and dive deep into a really fascinating puzzle from the world of nuclear physics. We've got a target in our sights, the half-life of a very specific element, Americium-234.
I mean, really think about that for a second. How do you even measure the lifespan of an atom? We measure our own lives in decades, years, days. But an atom? Its entire existence is basically a game of probability. So how in the world do you find its internal clock, its heartbeat, when it's just so incredibly tiny?
So, here's our mission today. We are going to crack the case of this decaying element, Americium-234. We're going to follow the evidence, track how it decays over time, and use all that info to find its unique internal clock. And that clock is what we call its half-life, that one specific moment in time when exactly half of the atoms we started with are gone. Okay, so every good investigation needs a key clue, right? A piece of evidence that cracks the whole thing open. For us, that clue is something called the decay constant. And trust me, it is the absolute secret to understanding everything about Americium-234. Now this decay constant, and you'll see it represented by the Greek letter lambda, it's not just some random number from a textbook. The best way to think about it is like an individual risk factor for each atom. It tells you the exact probability that any single nucleus will decay in a given unit of time. It's the fundamental rule of the game for this whole process. And here it is. This is our number, the critical piece of evidence. For Americium-234, that value is 0.00785 per second. Now I know that looks like a really, really small number, but don't let that fool you. That tiny value is the engine that drives everything we're about to see.
So, we've got our key clue. Now it's time to actually start tracking the evidence. What we need to do is predict how our sample of Americium-234 is going to change over time, second by second.
Okay, think of this as our official evidence log. At time 0, the very beginning of our investigation, we have a sample of exactly 800 undecayed nuclei. But what about after 20 seconds? Or 60? Or 100? Right now, all those spots are blank. It's a mystery. To fill them in, we need the right tool for the job.
And this is that tool. It might look a little intimidating, but it's actually an incredibly elegant formula. It lets us predict n, the number of nuclei left, at any given time t. See that N0? That's just our starting number, 800. And there's our old friend lambda, our key clue. So let's plug in the numbers and get this evidence log filled out.
Boom! And just like that, our evidence log is complete. Just look at the pattern taking shape here. After only 20 seconds, we're already down to 684 nuclei. Fast forward to 80 seconds, and we've only got 427 left. And by the 140-second mark, just 267 remain. This just shows you the relentless, but also totally predictable nature of radioactive decay.
Now, numbers in a table are great. They're super useful. But sometimes, to really see the story the data's telling us, you need a picture. So our next step as detectives is to visualize this evidence. We're going to plot a graph.
And it's actually a really simple process. All we do is set up our axes, we'll put time on the bottom, the x-axis, and the number of nuclei on the side, the y-axis. Then we just plot the points from our table and connect them all with a nice smooth curve. And what we get is this beautiful sweeping curve. This is a classic exponential decay curve. And I want you to really look at its shape. See how it's super steep at the beginning? That's when a ton of nuclei are decaying really fast. But then, as time goes on, the curve starts to flatten out. The decay doesn't stop, not at all, but the rate slows way down. And that makes sense, right? There are simply fewer nuclei left to decay.
Okay, we've collected the evidence. We've visualized the data. We are now at the final stage of our investigation. It's time to finally solve this thing and find the answer we've been looking for this whole time, the half-life.
So let's be super clear about what half-life actually is. This is really important. It's not the time it takes for all the atoms to decay. I mean, theoretically, that would take forever. No, half-life is a very specific milestone. It's the exact amount of time it takes for precisely half of the radioactive nuclei you started with to decay. So visually, here's our target. We started with 800 nuclei. Simple math, right? Half of 800 is 400. So our whole mission right now is to look at our graph and find the exact point in time when the number of undecayed nuclei hits that magic number, 400. And there it is. We find 400 on the vertical axis.
We trace our finger over to the curve, and we drop straight down to the time axis. The answer? 88.3 seconds. That right there is the half-life of Americium-234. Case closed.
All right, so we found a number, 88.3 seconds. Cool. But so what? Why does solving a case like this actually matter? What does knowing an element's half-life let us do out here in the real world?
Well, it turns out this one concept is incredibly powerful. I mean, it's the entire basis for carbon dating, which lets us literally peek into the distant past. It's used all over medicine, for everything from medical imaging to cancer therapy. Geologists use it to date rocks and figure out how old the Earth is. And it is absolutely critical for making sure nuclear power plants are safe. Understanding this internal clock is the key that unlocks all of these amazing technologies.
And that kind of brings us to a final, bigger thought. We just used a pretty straightforward formula and a key clue to predict and understand the invisible process of an atom decaying. So it really makes you wonder, doesn't it? What other invisible processes out there, maybe in biology or in finance or even in how societies change, what else could we understand and predict if we could just find the right key clue?